minds rise and soar. Use your own AI, we'll explore. Help the future hand in hand in this tech-driven wonderland.
Okay, hello everyone. We have a special episode today. We have a reading group about a paper Alex will introduce in a second, and we have a near AI team joining as well to discuss it. So I'll let Alex to take it away.
Okay, you can hear me, right?
Yep.
Okay, awesome. So the paper we will be discussing today is called this one, the era of 1-bit LLMs. It's about training large language models with without multiplication, using only ones, zeros, and minus ones for weight matrices. Before we get there, let's do like a very quick recap. Let's spend like a couple of minutes to remember how transformers work and what components they have. So we have a stream of tokens coming in. Each token is an integer. It's an integer from somewhere from 0 to, let's say, 60K, the number of tokens in the vocabulary, where those would be like the most common combination of bytes, right? So every individual byte is a token, the is a token, cat is a token. And then the first thing it goes into is called an embedding. An embedding maps those integers into the vectors of size, what is called D model. And the D model is the size of the vector that represents an internal, I like to call it the state of mind of the model. And as the sort of information flows through the transformer, at each point, the state of it is represented by a vector of D model floating point numbers. All right, and then many times, this vector will go through a like a single transformer layer. Many times. And then at the end, it goes through what is called an unembedding. Where in the unembedding, it goes back from a vector of size D model into the space of tokens, right? So if you have 60 tokens, the unembedding will be effectively a matrix of size D model times the size of the vocabulary. And it will return you a vector of size and vocabulary where every element is proportional to the logarithm of the probability that that token should be sampled, right? And then you exponentiate them, you get the actual probabilities. Cool. And every transformer layer consists of two parts. The first part is called attention, right? And then attention, that's where you mix the information between tokens together, right? So like if the later token enters here, it goes into the attention. So internally here, it's put into attention and MLP. Right, so in the attention, you start by multiplying this vector of size D model, the input. Let's call it X. You multiply by three matrices. One is, let's call the first one QW. Sorry. Yeah. Or like other good times. Let's see. Will this work? Yes. Then you have X times Q, QW, and X times QW. Right. So you get three matrices And effectively, K and V are keys and values that you computed for the future tokens, and Q are queries that you use to query keys from the previous tokens. I'm not going to go too deep into attention right now. What is important is that there are three matrix multiplications here involved. And then after you compute Q, K, and V, the actual output of the attention, if I don't mess it up, will be something along the lines of Q transposed times K times V, except that transposition probably goes here. Yeah, so you compute, sorry, and there's a sigma here. Sorry, not sigma, sometimes. Okay. So again, what is important here is that there's a matmul here, and there's a matmul here. And then MLP is effectively just matrix multiplication, some nonlinear function in the matrix multiplication. So in each transformer layer, we have 1, 2, 3, 4, 5 plus 2 from MLP, 6, 7 matrix multiplications. Then unembedding is a matrix multiplication, right? So as you send, as a single token goes through the transformer, the majority of time it spends, the majority of computation spent is performing matrix multiplications, right? And so when you run, like if you download Ollama and you run Llama on your Mac, the reason it is feasible, the reason it is somewhat fast, is that the matrix multiplications are not being performed in the full precision, not in FP32. It is usually performed in something much smaller. And even when you train the model, right? When you train the model, the GPUs, A100, H100, they have a very fast kernels. Not even kernels. They have a very fast processing units on the chip that can multiply 16-bit floating point numbers approximately 4 times faster than they can multiply 32-bit numbers, right? And so as you train the model, the forward pass, backward pass you do in for matmuls you do in BF16, not in FP32. That makes training 4 times faster. And after the training done, once you have the model, people quantize it to 16 to 8 bits, and I think some people even quantize it to 4 bits. And the question would be, in the ultimate, can we quantize it to a single bit, where every matrix, every element in the matrix is represented by 1 bit? And let's see why it is challenging and what can be done about it. So let's zoom in into a single matmul, right? So let's say we look into this one, right? So we have vector X here. This is the model. And usually we don't look at a single vector, we look at a bunch of them. So there's your whole context window of data, right? So if you doing inference, you feed the prompt. Let's say the prompt is already 100 tokens. So this is your 100 tokens, your prompt. We call it, let's call it context. And this is multiplied by the matrix of size D model by D model. And after the model has been trained, there's this a matrix of size D model by D model of either FP32s or BF16s. So it's either 2 bytes or 4 bytes per element, right? So it could be like something like 0.6, 0. I don't know. And effectively, what we're saying is we say, hey, if we slightly lose precision here, right? If we compress every element to the fewer number of bits, the overall output of the model will not be affected that much, but the performance of the computation will be improved significantly, right? And we would, during the quantization, we would compress every element, let's say, to 1 byte, so to 8 bits, right? And then each of them will lose some amount of precision. but like overall, the performance of the model will not drop that significantly because, especially if you round them stochastically into different like some of them you round to the element that is smaller, some of them to the element that is higher, and if the D model is large enough, like on average, it is not that far from the output you were supposed to receive in full precision. And people measured it, and it was good enough for 8 bits, maybe not that good for 4 bits, but once you go to the lower number of bits, it gets worse and worse, right? And to see why, I think it's somewhat helpful to look at like what is it even that we're losing when we quantize, right? So if you look at the BF16, right? So let's say the model was trained in BF16, or rather, let's look at FP32 first. Okay, so FP32, you have 32 bits, and out of 32 bits, you will have. Let's think about it. I think I closed it already, but I think you have something along the lines of 8 bits of exponent, 1 bit for the sign, and then you would have how many left? 32 minus 9, 23 bits of mantissa. I could be a little off here. It could be like 10 and 21 or 11 and 20. I don't remember exactly. But importantly, so mantissa is what gives you the precision, and the exponent is what gives you the range, right? So you can trade one for another, right? In the extreme, you can imagine having, 31 bit of mantissa. That effectively be an integer type. Or you can imagine having 31 bits of exponent, which will give you a massive range, but practically no precision. And in a P32, it has quite a bit of range and quite a bit of precision. So that's there is no real trade-off there. But once you go to lower precision types, the trade-off starts being more and more pronounced, right? So if you go to 16-bit types, the default 16-bit types called FP32, sorry, FP16, would have 5 bits of exponent and 10 bits of mantissa. And that gives you decent range, decent precision, so 10 bits of precision, but very, very low range. And the problem is that quite a few values that you would actually encounter during training would not fit into the range of FP16. So what people do instead is they use a different data type called BF16 that has longer, so it would be like here, right? It would be 8 bits of exponent, 7 bits of mantissa. So that gives you, assuming my FP32 was correct, that gives you as much range as FP32, but much fewer precision, right? So effectively, all the bits that you trade as you go from FP32 to FP16 are taken away from precision. None of them are taken away from range. Cool. So BF16 is known to work pretty well for training, right? Majority of training happens in BF16, right? So BF16 is, the model is trained in BF16. So clearly, during inference, BF16 will work just fine. All right. Okay. So as we go to BF to 8-bit, we get one signed bit, and then you have two major options. Effectively, you either do 4 plus 3, or you do 5 plus 2. 5 bits of range, 4 bits of precision. So notice that as you go to 8 bits, right? So in BF16, there were 8 bits allocated for the range, right? So that is already more than you have total, right? So you will have to significantly reduce the range, and barely anything is left then for precision. And I think I'm actually not quite up to speed in terms of what people use for BF8, but either of them is very limiting. So this data type, the whole range is like from minus 400 to plus 400, give or take. And this one I think is from it's something like you have it here, practically from minus 57K to plus 57K, right? So in both cases, the range is pretty low already, and the precision is like, the precision you have is 2 or 3 bits. So what is important is that, like, it's quite natural to assume that for quantized model to work, the weights need to be at least somewhat close to what they were, right? So as the amount of precision you have goes lower and lower, the weights deviate more and more from what they should be, right? So like as you go from 2 bytes to 1 byte, you already will be quite far from the actual value that you have here. But if you imagine going to 4 bits, right? In 4 bits, you would still have 1 byte per sign, right? So you have a total 1 bit per sign. You have total of 3 bits for your exponent and for your mantissa, right? So like clearly you will deviate very far from the values, right? And in the extreme case, if you have 1 bit, then you literally just have the sign, right? 1 bit. You have the sign. You have no exponent and no mantissa, right? So and in practice, I guess people tried it, right? And if you quantize the model to a single bit or even to 2 bits, the model does not perform well, right? It loses its capabilities. So what can we do? So what the paper suggests to do, and there was 2 papers in a succession. The first one was called the first one was literally using 1 bit per weight, and this one is pre-Llama, right? It's October 2023. I think this is even pre-ChatGPT, or like I don't remember when ChatGPT came out. Was it November or October? But it's like wait. No, I'm saying it wrong, right?
It was 2022.
Yeah, okay. I'm saying it wrong. So this is post-Llama, right? Llama was 2022 as well. Llama was early 2023. Okay, anyway. And in this paper, it boils down effectively to the following. And this is the paper that introduces the whole concept. It boils down to the following. They say, instead of quantizing the model after the fact, what if we train it already with the idea of every weight being a single bit, right? And it's there was a reason why I drew the whole transformer at the beginning, because it's worth mentioning what they do quantize and what they do not quantize, right? So a couple of things they don't quantize. They don't quantize embedding to 1 bit. And the idea here, I think that it is important for the weights, like for this vector initially, to be high precision, right? So if you quantize the embedding, then your mental representation of every token from the get-go will be effectively binary. It will be a D-model bit number, which is not quite what you want, right? So they do not quantize embedding, and embedding is fast anyway. At least they don't quantize it to a single bit. They do not quantize unembedding to a single bit, or a thing at all, with the reason being that after you do unembedding, you want to sample, and ideally you want sampling to be done in high precision. They do quantize each of the parameter matrices, right? So you query projection, key projection, value projection, and both matrices in MLP are all quantized to a single bit. And they do not, for this product and for this product, they do them in full precision. Or by full precision, I mean presumably BF16. They don't do them in low precision. Okay. And when I say quantize, they do not quantize matrices at rest, meaning that the actual matrix they train, the actual QW, KW, and VW, and the 2 matrices in MLP are actually high precision matrices, right? They during training they are stored in at P32 or BF16, and they trained in high precision. However, what changes is how those matrices are applied on the forward path. So on the forward path, instead of multiplying the the input vector by the matrix itself. They quantize matrix on the fly, right? So the matrix is quantized before being applied to one bit, and then they multiply the matrix, the input tensor by the quantized matrix, meaning that during inference, you don't need to know the high precision matrix anymore, right? Because during the inference, you only have the forward path, right? So during inference, you will only be multiplying by a 1-bit matrix. But during training, the matrix is full precision, right? So you can apply gradients. All right, so let's go into a little bit more of the detail, right? So let's zoom in into a single matrix multiplication, right? So we have this. Let me move it. Oops. Okay, so we have an input tensor and a matrix that we multiply by. So this stays. I cannot do this. Like this. Okay. So we have the same input, and we multiply it by a matrix. So the matrix changes specifically for every weight. In the original 1-bit paper, they would apply the following transformation. They would subtract the mean. So they would compute, it's the mean of the whole matrix, right? So they compute the average value of the whole matrix, subtracted from every element, right? So now it is effectively centered around the mean. And then they would just take the sign of every element, right? So if the element after subtracting the mean is positive, it becomes 1. And if it's negative, it becomes -1. So let's say the mean was like, something like 0.2. Right? And this element will become 1 because it's bigger than mean. This element will become -1. Right? And so on average, you will get half ones, half -1s. And then you multiply the input tensor by this matrix of 1s and -1s, you get the output. Now, ideally, you would prefer the output to have more or less the same distribution as it would have been if you didn't quantize. So in the original paper, where is it? I do not see them anywhere compensating for the subtracted mean. I guess the expectation is that mean is approximately 0, which is not a potentially completely unreasonable expectation. But they do multiply by what they call a scaling factor beta, which is not described anywhere, but it's presumably the same mean. So let's say we multiply again by the mean. You can imagine if you replaced every element in the matrix, or rather, it's not going to be mean. It's going to be the mean of the absolute value, right? So if you imagine if you replaced every element in the matrix with 1 and -1, and then you multiply by regional matrix, and you multiply by the matrix that only has the signs, and let's say for the sake of simplicity that the mean was 0, right? So then the output will be if the average absolute value was 1, then the distribution of the output will be approximately the same, right? If the average absolute value was 2, then the output will be approximately twice as little, right? So effectively, you want to multiply later by the average absolute value to get to the same, more or less, distribution. And presumably beta is, in this particular case, and for the second paper that we're going to switch to in a second, they do have code, so we will see this is more or less what happens, right? So effectively, you replace. So if before output was equal to x times w, right? Then the new output would be equal to x times, let's call it binarized w, right? and then you would times mean, something like this. Cool. Now the problem with this is that this operation, this one, is not differentiable, right? So as you multiply, so as you compute the forward path, you want to compute the backward path. The backward path should be the derivative of the function that you apply in the forward path, but this binarization step is not differentiable. You cannot really compute the backward path. However, what you can do is you can say, well, because the output of this step is approximately, has the same distribution, more or less, as the multiplying by the matrix itself, we can pretend that binarization never happened on the backward path, right? So you compute on the forward path, you will quantize the matrix, multiply by the quantized matrix, multiply by the scaling factor, and on the backward path, you will pretend that never happened, right? You will just literally pretend that. So on the backward path, you will compute the gradient of the, you will just say, hey, like the gradient of W is equals to, gradient of the output times input transpose. I think this is how you compute it. Plus minus order and transpositions. Right, so you just completely ignore that. That is called a straight through estimator. And in fact, it says, hey, we're going to estimate the gradient of the weights and of the inputs as if, by estimating, with this non-differentiable function, with this fully differentiable function, which is just a matrix multiplication. Similarly, you would say like gradient of the input is equal to, I think it would be something similar, gradient of the output times. We transpose or something like this. I'm probably doing it wrong. Anyway, cool. So that's for weights. Now, as I mentioned before, so during training, you don't save that much. You do save a little bit, right? Because now your forward pass is faster, right? During forward pass, you do not do this matrix multiplication. You quantize the matrix and do a much faster operation. But during backward pass, you don't save anything because you still do 2 math moves to compute the gradient of the weights and the gradient of the input. But during inference, the backward pass doesn't exist, right? So this doesn't exist at all, right? You only compute the forward pass, which uses the quantized matrix. And as a matter of fact, you don't even need to store the original matrix. It is not necessary during inference. You only store the quantized matrix, meaning that you use significantly fewer memory. You use 1 bit per weight. And for the forward pass, you can use a custom kernel or even custom hardware, which doesn't need to do any multiplications, right? It only needs, like if you think what happens, if you think through what happens as you multiply by this matrix, right? You have some input vector, right? It has like some value, say ABCD, right? At every step, you start with accumulator equals 0, and at every step, if it's a 1, you add the value. If it's -1, you subtract, right? So there's no multiplications involved whatsoever, right? And there was the second paper where it simplifies quite a few things, and it introduces one other value, which is 0. They effectively say, instead of only having 1s and -1s, we're going to have 1s, -1s, and 0s. The benefit, there are 2 benefits of doing that. The first benefit is that you have more precision, right? So now you have 3 values, which increases the precision of your model. But the second benefit is that if on average 1 out of 3 values is 0, which is what they observe eventually, that the distribution of 1s, -1s, and 0s is uniform, more or less, then 1 out of 3 times you perform no subtraction or addition, right? So you reduce the amount of computation by 30%. And they simplify the computation. They do not subtract mean anymore, you will notice, right? So they do round clip, and round clip just starts from so like x here would be a single weight, and they do not subtract mean, they just yeah. So effectively they start with the weight matrix. They divided by the mean of the absolute value, right? Clip it to from -1 to 1 and round it, right? So rounding effectively means it becomes either -1, 0, or 1, whichever was the closest. So there's no more mean subtraction. And one thing I didn't mention is they also quantize the activations. And they effectively say we want it to be between. They want activations to be one byte, right? So 8 bits, and they. I don't think they do anything particularly fancy there. It's just they just literally squish all the values into the range from -128 to 128 and round it. Okay, so let's see how it looks in the code. They did publish a PDF that has a PyTorch implementation of it. So let's take a look and see how all of what we just discussed maps into code. So weight quantization, right? So you have a matrix W. Matrix W is a full precision matrix that you have in memory. Okay, so we compute the apps mean, right? So that corresponds to effectively computing this. I don't know how to pronounce Greek letters. Right. So this is effectively to prevent division by 0. If it happens that your whole matrix is all zeros, you don't want to end up dividing by 0. So W times scale means W divided by the absolute mean value. Then you round it, right? So what happens here is that after you divide every value by the apps mean, you will get something. The absolute value of every element will be on average 1, right? So after rounding it, you will get zeros, ones, minus ones. You still can get some other values, right? So the fact that the mean value is on average 1 doesn't mean you don't have outliers, right? And then it is clamped between -1 and 1. And let's ignore this divided by scale yet. So this part effectively computes the quantized model, right? And so what you would do then is that you would separately have the scale factor, right? And on the forward pass, you would apply the quantized model, right? And then later you will divide by scale. But during training, I guess they short-circuited and they divide by scale. The matrix itself is divided by scale, right? So they do not use the custom kernel. They just use the regular math mode. So might as well multiply by scale right away. Scale is a scalar, right? It's a single value. Right, so they divide. So effectively, they end up having not. So the matrix, the output, the U here will not be the matrix containing -1s, 0s, and 1s. It will be a matrix containing -1 over mean absolute value 0s and +1 over mean absolute values, right? But ideally, when you train the model and ship it to people, you will publish this matrix and this scalar separately, right? So then you can use the custom kernel or custom hardware to apply it, and then you divide separately. And activation quantization is similar. It's effectively the same function with a couple of changes. One is they divide by the maximum value, not mean. right? So this is more reliant, I guess, on the activations being more or less uniformly distributed. And you will notice it's per, that makes sense, it's per token. So here scale is it's a single scalar, right? So for the whole matrix, you compute a single value. But here it's per token, right? So scale is a one value per token, right? But the transformation is the same. The difference here would be that the output of this is not, the mean is not 1. The mean absolute value now is 127. So when you round it, you will round it to something between, minus 127 and 127, and then you clamp it. And again, divide by scale. This is something that potentially will be done as a separate step. Cool. And in terms of implementation, the implementation after that is very simple, right? So you build weight quantization, you build the activation quantization. The whole function, the whole layer now boils down to having, it has one parameter, the weight. You compute RMS norm. This is the same thing that will be done in Llama, right? So Llama begins every layer by computing an RMS norm, right? And then let's see what happens, right? So they say X quantized is equal to X normalized plus. Okay, so let's go through this. This is an implementation detail, right? So you will notice it has X norm minus X norm, right? So they will cancel out. And then it has activation quant of X norm. So this is the quantized X norm, from minus 128 to 128. So the reason to let's get back to it in a second, but for now, X quant is just quantized X norm, right? These two things cancel out. Then we multiply, then the same hack, you see, there's W minus W that cancel out, and there's a weight quantization, right? So X quantized is a quantized input, W quantized is a quantized weight, and then they compute the output as a product of quantized X and quantized W. And this hackery with adding and subtracting X norm is effectively a way to implement the straight-through estimator that we discussed, where we want to compute the gradient as if quantization never happened. So detach effectively means, hey, do not use this for backward pass, right? So if you look at what the backward pass will see, for the backward pass, X quant is equals to X norm, and W quant is equal to W, and then Y is the product of X norm and W, right? So on the backward pass, the gradient will only see W and X norm, and effectively, the gradient of X norm will be a product of the output gradient and W quantized, and the product and the gradient of W will be product of the X quant and output gradient, right? So this little trick with adding and subtracting X norm, but then detaching one of them, allows you to implement straight-through estimator in a very concise way, right? And then once you have this layer, which is, what is it, like 30 lines of code, maybe less, 20 lines of code, all you do is you replace the linear layer for query projection, key projection, value projection, and the two MLPs, and the two matrices, matrix multiplications in MLP with bit linear. It's called bit linear. And then you train the model, right? And the idea here now that because the model is, as you train it, because the model is already quantized, right? It learns the weights that will work with the quantized model, right? So by the end of the training, you get a model that performs well being quantized to a single bit. Right? And there's a couple of other interesting things here. One is that at the beginning, if your learning rate is, if you start with the same learning rate you would start when you train a llama model, the training will not pick up, because applying a small perturbation to the weight does not, like, effectively, you need to apply quite a bit of change to the weight for the sign to to flip, right? And if you start with a low learning rate, you apply small changes to the matrix, very few bits flip, right? So the training does not do much. So they have to start with a much higher learning rate. To the extent that the learning rate they start with, if you started training llama with the same learning rate, like a full precision llama, it will diverge, right? So effectively, empirically, this 1-bit model is more stable at the beginning of training, which is nice, right? But then they, I believe, like closer to the end, they actually go to a pretty low learning rate, and at that point, the training goes pretty well. Okay, I think that is all there is to the paper. The cool thing is not only the fact that there is no interested in this, and there's a good chance we're going to try to train something like this. Is that allows you to have a much bigger model that fits into memory of of a machine, and the inference could be much faster, right? So if you have a machine without a GPU accelerator, not having to multiply things is a highly desirable aspect, right? And so that can enable more people to benefit from more sophisticated models.
There's also energy analysis on operations on bits versus 8 bits, and it's like way lower energy usage. And so for mobile devices, for example, if you run such a model with this ternary weight, you potentially have way less energy exhaustion, which is probably one of the bigger issues actually for running on edge LLMs right now.
And I guess it also makes it more viable to run models. Like, I don't know if it's a good idea, right? But it does make it viable to run models on SGX on the CPU, right? So if you trust, like if you have a cloud with a bunch of SGX devices, you can run a 1-bit model. It could become a viable thing if that's something that is important to you. Cool. Are there any questions, comments?
And yeah, it can be custom FPGA or ASIC as well.
Yeah. So like if the model is shown, everything I showed right now is actual as of 5 months ago. I actually did not find if anyone managed to train a large model. It's been several months, so there's a chance someone already trained it. If nobody did, we can definitely try it, right? And if it is if a larger model is functioning well, then like investing into building an ASIC that does it very fast is a worthy endeavor.
Yeah, I thought it was
go ahead.
Interesting to look at this from kind of a top-down perspective. It makes a lot of sense to push towards binary. We've been doing that, for many years as engineers. I mean, the initial computers, used a lot more different voltages to represent different numbers. Like, 0 to 10 volts, great. We'll have, base 10. But it was, it was a lot simpler to push that down towards binary, partly, because of just noisy electronics, but we also got some things that kind of dropped out of binary that, we now you're working with Boolean logic, and with powers of 2, you get fast Fourier transforms instead of Fourier transforms. So I feel like logically it makes a lot of sense. And then it's also kind of similar to the brain, right? You've got brain activations, or kind of a binary type of thing. So yeah, makes sense to go this direction. And then looking at this paper, it's like, okay, ternary. Why would you go ternary from like just a conceptual level? And you had mentioned the kind of quantitative advantage that a third of the weights are 0. That makes a lot of sense. I was trying to think about kind of the qualitative differences between like 1s and 0s and -1s. Those give you some different sort of things. Off is very different from on. If you were asking a neuron's opinion, do you have an opinion on this feature, or like no opinion? The negative seems interesting in terms of like being able to have inhibition. You can have a neuron that's inhibiting other neurons in your system here. So
yeah. So it's interesting. So first of all, there's a disadvantage, right, to having 0, because now you need to have 2 bits per weight. Right? So the memory footprint is you either need some hackery to compress it to not actually spend 2 bits, or you're wasting like the memory footprint now is 2x. And something interesting, something Ilya mentioned 2 minutes before we went live, is that the paper does not actually compare 158 bits to 1 bit, right? So nowhere here in the results is bitnet 1 bit. So it's interesting, right? It would be a good experiment to try to compare 1 bit to 158 bits. See how they compare.
Two things I think are like worth pointing out is like one, in your diagram, Alex, you're showing like -1 and 1, but there's also zeros. Effectively, you don't need to load those weights into memory because they shouldn't affect, like they won't affect the output. And also in the PyTorch code, they show using linear, but yeah, as you mentioned, you can use like a better kernel to compute the forward pass. Like it would probably just end up being a select and a sum, effectively. And that would be faster than doing a matmul in general.
Mm-hmm.
So there's actually another paper that came after in June. I just sent it here. And it's pretty much matmul free transformer. And it is pretty much toward what you're just talking about, which is then going in, okay, well, if we're already in bit space, like let's just remove matrix multiplications completely and replace them with ternary accumulators and a few other tricks. And so I think it's pretty much in that direction of like, and they have a FPGA implementation, at least the reference in the paper, that presumably allows to have this.
Yeah, okay, so this is the same bit linear, right? It's not a different.
Yes, yeah. So that's what I'm saying. They took that and they kind of expanded it without multiplication.
Yeah, it's worth mentioning. I didn't think too deeply about it, but I think on GPU, the fact that zeros are not resulting in a addition does not give you that much, right? Because on GPU, like all the processors are doing the same work, right? So if you have if some of them are 1, some of them are 0, some of them are -1s, it will be something like, if it's 1, add, if it's -1, subtract, and all of them will have to go through those branches. Right? So 0 doesn't save you much, but on a custom hardware, presumably you can. Where do I have it? Yeah, presumably you can have it. Saving you quite a bit of time. Do they build it for like is it for FPGAs or?
They have, I think, both the PyTorch code and FPGA.
Also, depending on the distribution of like the number of zeros, then you can also save on memory.
But it's not easy.
It's hard to do on GPU. Yeah, it's hard to do on
GPU. It would be hard on GPU, but for an FPGA, you can like save on space.
Yeah, I guess in the short term, if we're simulating this instead of having an FPGA, is it still worthwhile? Does it have enough gains?
I mean, I think on the mobile device is just the amount of energy exertion is so much less. Like I'm looking at there's a comparison in the 1-bit paper, and they show that on a 7-nanometer processor, the addition on 32 bits is compared to on 1-bit. Let me do a division. Is like 40 times cheaper to do 1-bit, and multiplication is like 300 times cheaper. So you're potentially just getting, such a massive energy. And I've heard the same thing from like folks who run on like LLMs on phones, that they're very interested in this types of models because it's just like so much more energy efficient. Because right now, if you try, like even if you're running 3B model, I mean, especially if you're running 7B, like your battery will just gonna die. And whoever ran GPUs, like when you actually like spinning up all the training process or inference process, right, you can see the energy usage just going through the roof, right?
I want to open up the discussion on limitations that come with like this model, this approach. Sorry, and like for example, you said, Alex, that like for the weights to flip in the model itself, it takes like a higher learning rate at the beginning because it's like insensitive. And so, what would happen in case of fine tuning, for example? What do you believe?
Yeah, that's an interesting question. Let's see if they discuss fine tuning at all. Not much. So presumably, well, let's begin with the simple fact. If you only open source this, then of course fine tuning is out of question, because you do need the high precision weights, right? But naturally, I think it makes sense that if this model gets open source, or even if it gets open weights, it makes sense to open weight the high precision weight matrix, right? Then presumably fine tuning will work, right? Likely you will have to start with a higher learning rate than usual. But the same training loop you apply during training should potentially work with the fine tuning. That's something to experiment with, to see if fine tuning picks up. Because I assume that it's an interesting question, right? Because you were like, as you apply, even with a higher learning rate, as you apply the gradients, a lot of weights will not flip the bit, right? So it's like when you train on high precision, you apply the gradients, every weight is changed, right? You get a lot of like on the next step, you have a model which sort of assimilated quite a bit of information from the previous gradient update, right? But if only a subset of bits flip, right, that means that a bunch of gradient updates did not affect the model at all. So I would expect that during fine tuning, with the same number of samples, it might require larger number of samples to get to the same level of quality. But that's something that's something to play with. So it makes sense to try to train like I don't know, a largish model and try to fine tune and see what happens.
And could you think of any like other kind of limitations that could come with this kind of models? It's a hard to answer question.
Yeah, again, it's an easier question to answer with experimentation, right? So we can.
I mean, it's actually interesting because indeed you need to like get over a bigger hurdle. It might be interesting to see which bits are flipped when you are updating on a single batch, because that may be more informative than like looking at gradient updates in regular models from just interpretation perspective. But I think I looked around the internet. There's a few different people who've done fine tuning, like instruct fine tuning, as well as LoRa. Seems it works. I mean, there's a little bit of handling of LoRa required to quantize the LoRa itself.
So LoRa gives you. So what is LoRa in this case? You will have two quantized matrices on top of the.
Yeah, it seems like they are
Fascinating.
There's a link, I'm sure. There's a bit LoRa layer.
Is it the same Roma? It's not the guy who built Tornado Cache, right?
I mean, pivot to AI, right?
Yeah.
But yeah, definitely need some experimentation. Get this set up. But yeah, I think it'll be really interesting to see the difference after like one batch and kind of to understand a little bit more, like, because indeed, yeah, you from every single update you have a little bit of difference in all weights every update, which is really hard to interpret, and so you kind of need to do. Like if you want to see how much information is extracted from a single batch, you really need to get like a lot of kind of A/B testing, inferencing. Here, you can actually then isolate some of the things, some of the capabilities potentially, because if you are as you're training the model, you can see when it gets. Like when it starts getting some capability, right? Like you literally run an eval of that capability at every step. And then if you go and see kind of what was the batch that led to it, what was the updates, there can be interesting like analysis around this. If you have like set of capabilities and you're kind of testing for them. So yeah, just it can be really interesting for just like understanding more how information is stored and how some of the more reasoning capabilities are being emerged.
Yep. Okay, we're getting close to the 1 hour mark. Any final questions or comments people have? I guess no. Okay, cool. Thanks everyone for coming and watching. And I guess there's going to be more of those coming. in the future weeks. So stay tuned.
Yeah. If you have any ideas for papers, drop them in comments/replies. And thanks, Alex, for deep dive.